We previously saw that a function is continuous at a point x is equal to a if the limit as x goes to a of f of x is equal to f of a. Right? So in other words, as you approach the actual point, as the x value approaches the point, the y values are also approaching the output. So in other words, you can draw the function without lifting your pencil. And we also saw that recently that a function is differentiable at a point x is equal to a if this limit, the limit as h goes to 0 of f of a plus h minus f of a divided by h exists. And this limit is just f prime of a. So in other words, a function is differentiable as long as there's no jagged edges in the function at that point. Today we're going to look at a theorem. So this is an important theorem that says a differentiable function is also continuous. So in other words, if a function is differentiable at a point x is equal to a, it must also be continuous. So in other words, differentiability implies continuity. So the quality of being differentiable implies that the function must also be continuous. Now the converse is not necessarily true. So in logic, the converse statement is the statement that is obtained by reversing the logical direction. So here we have differentiability implies continuity. The converse statement, so the converse of this would be continuity implies differentiability. Now this statement is false. And we can prove that it's false with a simple counterexample. So if we consider the absolute value of x, which looks something like this, so this function is clearly continuous because you can draw it without lifting your pencil from the paper, and yet its derivative, it fails to be differentiable at the origin. So here you have a function that's continuous at the origin, but not differentiable. So continuity cannot imply that the function is differentiable. So differentiability is a stronger condition than continuity alone. So a function can be, in fact, different or continuous and have lots of places where it fails to be differentiable. In fact, there's a higher result from a field of mathematics called functional analysis that says that there exist functions that are continuous but nowhere differentiable. So that means they're not differentiable at any point on their domain, which is, you can't even imagine this thing that somehow it's continuous, you can draw it without lifting your pencil, but there's no point at which it is differentiable. So at every single point it's like a jagged edge. So it must be some sort of fractal type deal. I can't imagine what that might look like. But according to result in functional analysis, not only do those sorts of functions exist, functions that are not differentiable anywhere, but yet they are continuous, but most functions in certain function spaces actually have that property. But that's more of an abstract result, and those are kind of not the normal functions that we study in calculus. But all you need to really do is remember this basic example of the absolute value of x. You can see that it's continuous, but it's not differentiable because there's no tangent line at the origin. Now, this theorem, though, it says the opposite. It says differentiability implies continuity. So if the function is differentiable, it must also be continuous. So in general, you always have to pay attention to which way a theorem, the logical implications work. So another example, practical example of the converse statement not being true is the following. So suppose that you were to say this: if my car is out of gas, then it is not running. True statement. So assuming that you don't have an electric car, assuming you have a gasoline engine, if your car is out of gas, then it is not running. Straightforward enough. What's the converse statement? The converse statement would be, if my car is not running, then it's out of gas. Well, clearly the converse is not true. The converse statement is false. A car can be not running because it's switched off, but there can still be gasoline in the tank. So the one direction works. If the car is out of gas, then it's not running. The converse is not true. It's not a true logical implication. If the car is not running, then it must be out of gas. That's a false statement. So here, differentiability implies continuity, but continuity doesn't necessarily imply differentiability. So to see why this is true, we're going to prove it. So we want to show that differentiability implies continuity. So here's the proof. So first of all, f is differentiable at a point, x is equal to a. So therefore, the limit as h goes to 0 of f of a plus h minus f of a over h exists. And so we'll actually give this a name. We'll say it's equal to f prime of a. So the derivative at this point exists. And from that, we need to show that the function must be continuous. Well, in order for the function to be continuous, so first of all, let's rewrite this. So this is really equivalent. If we say that x is equal to a plus h, right? Because a is just a fixed constant. So as h goes to 0, that's the same as saying x goes to a. So we can actually rewrite this limit by saying the limit as x goes to a of f of x minus f of a over x minus a exists and is equal to f prime of a. So this limit exists. That's that limit. Right. So this is the same as the standard way of writing it up there. Again, this is just, in fact, this is perhaps more direct. This is just your delta y over delta x, and then take the limit as delta x goes to 0. In other words, take the limit as x is approaching a. Well, from this, we want to show that the limit as x goes to a of f of x minus f of a is equal to 0. It's a minus sign there. Right, and that's equivalent to the limit as x goes to a of f of x is equal to f of a. So that's the continuity. So these are our two equivalent statements. So since f of a is a constant, I can also, toss that into the limit. So by subtracting this from both sides, I get the limit as x goes to a of f of x minus f of a. Now f of a is equal to the limit as x goes to a of f of a, because f of a is just a constant. So I can move this to the other side and rewrite that like this. So I want to show that this is equal to 0 using this equation right here. The trick is the following. So this limit right here, so let's make some space. So this is basically our differentiability condition, and this is our continuity. So the limit as x goes to a of f of x minus f of a, this is the same as the limit as x goes to a of x minus a times f of x minus f of a over x minus a. Right, because I multiplied and divided by a factor of x minus a, so these factors cancel out and the limit's going to be the same. Now, since the limit as x goes to a of x minus a exists, and since this limit exists, and we know that this limit exists because we're assuming the function is differentiable at this point. So differentiability tells us that this limit, so the limit of just this part, approaches a finite value. And similarly, this limit exists. So because both of the limit of this factor exists, and because of the limit of that factor exists, then by the limit laws, this is equal to the limit as x goes to a of x minus a times the limit as x goes to a of f of x minus f of a over x minus a. Now note that we cannot do this step if the function is not differentiable. So when one of the factors by itself, that limit doesn't exist, you can't separate the two limits as the limit of one factor times the limit of the other factor, like we did right here. But since this limit does exist, we can break it out into two separate limits, a product of two separate limits. And this one converges to f prime of a, and this one goes to 0. So it's equal to 0 times f prime of a, which of course is just equal to 0. So therefore, the limit as x goes to a of f of x minus f of a is equal to 0. But on the other hand, that's equal to the limit as x goes to a of f of x minus just f of a equals 0. So therefore, this limit, since this minus this is equal to 0, that's the same as saying this is equal to that, and that is continuity. So we started off with differentiability, so we used differentiability in order to separate this into two separate limits, and then that proves that the function is continuous. So that's a proof that whenever a function is differentiable, it must also be continuous.